Hello everyone, welcome again. In previous video, we have discussed how to find the complementary function of a linear differential equation with constant coefficient. We further discussed 4 examples on 4 different cases of complementary functions. Now, in this video, I am going to discuss the method to find particular integral of a linear differential equation with constant coefficient. As we know, the complete solution of a linear differential equation with constant coefficient is y equal to cf plus pi. So, the particular integral. Suppose the given linear differential equation is function of dy is equal to qx. This is our given linear differential equation with constant coefficient. Then the particular integral of this linear differential equation with constant coefficient is given by we transfer this multiplication term function of d in the right hand side and we express the particular integral as particular integral pi is equal to 1 upon function of d into qx. Now, the process of evaluation of particular integral is depends on the nature of qx. So, here we discuss 5 different cases of evaluation of particular integral based on the nature of qx, that is the non-homogeneous part of the differential equation. So, the case first is when qx is exponential function of the type e raised to ax. So, suppose the qx, the non-homogeneous part of linear differential equation with constant coefficient, is exponential function of the type e raised to ax. In this case, we have pi is 1 upon function of fd into e raised to ax. Now, to find or to obtain the particular integral, we have to replace d by a. Then, to evaluate the particular integral, we replace d by a. Then we get the particular integral is 1 upon function of a into e raised to ax. So, this is the particular integral when the qx is exponential function, provided function of a is not equal to 0. F of a must be not equal to 0. Now, in case if f of a is 0, in particular, if f of a is 0, then first we multiply this numerator by x and then differentiate this denominator function of d, this denominator function of d with respect to d, and then we put d equal to a. So, in case of f of a is 0, we get particular integral pi. First we multiply this numerator by x and then we differentiate function of d with respect to d, then we get f dash d. Now put d equal to a, then we get x upon f dash of a e raised to ax. So, this is the particular integral, provided f dash of a is not equal to 0. In case if f dash a is 0, then again we multiply this numerator by x, then we get x square here and we differentiate f dash d with respect to d again, then we get f double dash d and then we replace d by a, then we get x square by f double dash of a e raised to ax, provided f double dash of a is not equal to 0. So this is the process of finding particular integral when qx, that is the non-homogeneous part of the differential equation, is exponential function of the type e raised to ax. Now we discuss 3 examples. So our first example is solve d2y by dx2 plus 3dy by dx plus 2y is equal to e raised to x. So this is a differential equation. Further, it is linear because y power 1, dy by dx power 1 and d2y by dx2 power 1, and there is no multiplication term of y and its derivative. So this is linear differential equation of second order, and it is higher order. So coefficient of y is 2 constant, coefficient of dy by dx is 3 constant, and coefficient of d2y by dx2 is 1 constant. So this is linear differential equation with constant coefficient. So given equation is linear differential equation with constant coefficient, and therefore its solution is what? Y equal to CF plus PI. The solution of LDCC is y equal to CF plus PI. Now first we obtain complementary function CF, and for that we have to write auxiliary equation. So first we write this differential equation in form of differential operator capital D. So here we have d square y plus here we have 3dy plus 2y. So we take y common, and therefore the given equation also can be written as, so d square y common, 3dy y common, and 2y y common. So we get d square plus 3d plus 2y equal to e raised to x. So we express the given equation in form of differential operator capital D. So this is equation of the type function of dy equal to e raised to x. Now to find complementary function, we first write the auxiliary equation, and auxiliary equation can be obtained by replacing d by m in this function of d expression and equating to 0. So here we put d equal to m and equating to 0. The auxiliary equation is given by m square plus 3m plus 2 equal to 0. So this is quadratic equation in m, gives two values of m. Now factor of this quadratic equation are m plus 1 into m plus 2 equal to 0. So this gives m equal to minus 1 and this gives m equal to minus 2. So the roots of auxiliary equation are m equal to minus 1 and minus 2. Both roots are real, not contain iota, and both roots are distinct. They are different. One is minus 1 and other is minus 2. So this is the case of complementary function when the roots are real and distinct. Then the complementary function is what? C1 e power m1x plus C2 e power m2x. So the complementary function is C1 e power m1x, so m1 is minus 1, plus C2 e power m2x, m2 is minus 2. So this we get the complementary function. Now we find the particular integral, and for particular integral we transfer this product term function of d in right hand side. Then we get particular integral is 1 upon function of d, which is d square plus 3d plus 2 into e raised to x. Now this is the case of exponential function. Qx is what? Qx is what? Exponential function of the type e raised to ax. So we know in case of exponential function e raised to ax, pi can be obtained by simply d replaced by a, and here a is 1. So put d equal to 1 because e raised to ax, a is 1. So replace d by 1 in this expression, we get 1 upon 1 square plus 3 into 1 plus 2 e raised to x, and this gives 3 plus 2 5 plus 1 6, 3 plus 2 plus 3 5 plus 1 is 6. So we get 1 by 6 e raised to x. So So this is the particular integral. So this is the case of exponential function. So pi can be obtained by d replaced by a, and here a is 1, so we get 1 by 6 e raised to x. Now the complete solution of differential equation is y equal to cf plus pi. Next example is solve d plus 2 into d minus 1 whole cube y equal to e raised to x. So this is clearly a linear differential equation with constant coefficient, and therefore its solution is y equal to cf plus pi. The solution of LDCC is y equal to cf plus pi. Now first we find the complementary function cf, and therefore we have to write the auxiliary equation. Here the given equations is directly given in differential operator d. So auxiliary equation can be obtained by putting d equal to m in this function of d term and equating to 0. So to find cf, the auxiliary equation is m plus 2 into m minus 1 whole cube equal to 0. Now from here we get m equal to minus 2, and from here we get m equal to 1, but 3 times, because this is m minus 1 whole cube, that is m minus 1 into m minus 1 into m minus 1. So we get the roots of auxiliary equations are 1, 1, 1, 3 root from here, and 1 root minus 2 from here. So roots are real, but here we have 3 repeated roots. So for 3 repeated root, we write complementary function using the formula of repeated root, and this is distinct root. So here we use the formula of distinct root. So for 3 repeated root, the complementary function is c1 plus c2x plus c3x square multiplied by e raised to mx, and m is 1 for 3 repeated root, plus next root is different, so we use normal formula. Next constant is c4 e power m4x, and m4 is minus 2. So this is for 3 repeated root, and this is for 1 distinct root, and this is the complementary function of the given linear differential equation with constant coefficient. Now we have to find pi, particular integral. So for particular integral, we have to transfer this product term function of d into right hand side. Then we get the particular integral is 1 upon d plus 2 into d minus 1 whole cube e raised to x. So this is the particular integral. Now we evaluate the particular integral. So this is what? Exponential function of the type e raised to ax. So in case of exponential function, pi can be obtained by simply d replaced by a, and here a is 1, so d equal to 1. So now d equal to 1, we get 0 here. The function of d becomes 0. So this factor make the denominator 0, but this factor not make the denominator 0. So first we solve this factor, then we write function pi is equal to this factor we solve later, because this factor makes 0 denominator. So we write here now 1 upon d plus 2 into e raised to ax. Now replace d by 1 because of exponential function. So we get 1 plus 2, 3, and then we write 1 upon 3 into 1 upon d minus 1 whole cube into e raised to x. Now put d equal to 1 because of exponential function. To get pi, we replace d by a, and here a is 1. So d replaced by 1, we get f of d is 0. So in that case, when function of d becomes 0, what we do? We multiply the numerator by x and differentiate denominator with respect to d. Then we get d equal to 1 gives f d equal to 0, and therefore we write multiply numerator by x and differentiate this denominator with respect to d, then we get 3d minus 1 whole square e raised to x. Now replace d by a, and a is 1. So again 1 minus 1 is 0. So put d equal to 1, we get f dash d is 0. So again we multiply numerator by x and differentiate this denominator with respect to d. Then we get here x square, and this become 9, 3 into 9. So x square by 9, and differentiation of this denominator d minus 1 whole square is 2d minus 1 into e raised to x. Now because of exponential function, to get pi we replace d by a, and a is 1. So again we have 0. So put d equal to 1, we get f double dash d equal to 0. So again we multiply the numerator by x and differentiate this denominator with respect to d. So we get x cube by 18, and differentiation of this with respect to d is 1. So we get x cube by 18. This differentiation is 1 into e raised to x. Now all d eliminated. So this is our pi. Hence the complete solution is y equal to cf plus pi. And next example is solve d minus 1 whole square into d square plus 1 whole square y is equal to e raised to x. So this is clearly a linear differential equation with constant coefficient, and therefore its complete solution is y equal to cf plus pi. First we find the complementary function cf, and therefore we write the auxiliary equation, and which can be obtained by simply d replaced by m in this function of d and equating to 0. Then we get m minus 1 whole square, and here m into m square plus 1 whole square equal to 0. So to find the auxiliary equation, to find complementary function, the auxiliary equation is m minus 1 whole square into m square plus 1 whole square. So from here we get m equal to 1 2 times, because m minus 1 into m minus 1 gives m equal to 1 and 1. And here m square plus 1 is 0, then we get m square equal to plus minus iota. So 2 times we get plus minus iota. So the roots are 1 1 plus minus iota plus minus iota. So here 2 roots are real and repeated also, and the complex root, here alpha is 0, beta is 1, here alpha is 0, beta is 1. So real root are repeated, complex root are also repeated. So the complementary function, the cf is given by, for real repeated root we write c1 plus c2x e power m1x, which is 1. And for complex repeated root, alpha is 0, beta is 1, alpha is 0, beta is 1. So e power alpha x, alpha is 0. For complex repeated, we write c3 plus c4x cos beta x, and beta is 1, iota beta, so beta is 1, plus c5 plus c6x sin beta x, beta is 1. So for real repeated root, for complex repeated root. So this is the complementary functions. Now we find the particular integral, and for that particular integral we transfer this product term function of d into right hand side. Then we get pi is equal to 1 upon d minus 1 whole square into d square plus 1 whole square e raised to x. Now this qx is exponential function of the type e raised to ax. Therefore to get pi we replace d by a, and a is 1. So by replacing d equal to 1, this factor becomes 0, but this factor is not 0 for d equal to 1. So first we solve this factor, and then we go for this factor. So we write the particular integral particular integral is 1 upon d minus 1 whole square into 1 upon d square plus 1 whole square e raised to x. This factor not 0 for d equal to a, but this factor is 0. So we solve this factor later, but first we solve this non-zero factor. So due to exponential function, we get pi by replacing d equal to a, and a is 1. So 1 square is 1, 1 plus 1 is 2, and 2 square is 4. So we get 1 by 4. Now we write 1 by 4 constant outside. Then we have 1 upon d minus 1 whole square e raised to x. Now for exponential function, to get pi, we replace d by a, and a is 1. So 1 minus 1 is 0 here. So put d equal to 1, f of d becomes 0. So we multiply numerator by x and differentiate denominator with respect to d. Then we get x by 4 into 1 upon derivative of d minus 1 whole square is 2d minus 1 into e raised to x. Now put d equal to a. Because of exponential function, to get pi, put d equal to a, and a is 1. So again 1 minus 1 is 0. So put d equal to 1, f dash d becomes 0. So again we multiply this numerator by x. So we get x square here, and differentiate this denominator with respect to d. So we get 1 minus 0, that is 1. Derivative of d minus 1 is 1. So we get x square by 8. This derivative is 1 into e raised to x. So x square by 8 into e raised to x. And since all the d's are eliminated, so this is our pi. Hence the complete solution is y equal to cf plus pi. So these are few examples on case first of particular integral when qx is an exponential function of the type e raised to ax. We discussed both type of examples, when function of a is not equal to 0 and when function of a equal to 0. In next video we will discuss few more example on this case. So see you in next video. Thank you.